All right, good afternoon, everyone. Okay, so we have been talking about network layer and routing. We've been talking about network layer, and we've done all the topics up to the main function of the network layer, which is routing. So today we're going to talk about routing. So before I go, are there any questions on anything that we've done so far? So, right, so some of the important ideas there are a router has to do forwarding and routing. So we've talked about forwarding already. And in that context, we talked about IP addresses and longest prefix matching, right? So remember, the sort of the basic idea there is that IP addresses are hierarchical. And so this hierarchy means that two hosts that are geographically close to each other have similar IP addresses. And similar meaning the network part is similar or the same, right? And the network part we said was the first so many bits, like it's the prefix of the IP address, the first part. Okay, and then we use that to do, in a router to do routing to forward to the correct interface by doing longest prefix matching, right? And so that was the takeaway message, kind of from what we've done so far. Right now, along the way, we talked about NAT, we talked about IPv6, and some of the other, like when we went to the header of IP, we talked about some of the functions that are also implemented at network layer. Okay, so are there any questions about that? So today we're going to talk about routing. Okay, we're going to talk about two strategies to finding good paths, right? Two strategies for routing, right? One is called link state, and the second is called distance vector. Okay, so these are going to be two core routing strategies on which most of the routing strategies used in modern networks are based upon. So I'll talk about those two ideas first. All right? Okay, so this is just to remind you, right? This is the forwarding table driven by the routing algorithm. So we'll talk about the routing algorithm now. Okay, so when we talk about routing, we're going to abstract the network as a graph. Okay, a graph has vertices and edges, and it has labels on those edges. So if you look at this graph here, there are 6 vertices. Each of those vertices represents a router in my graph, in my communication network. Okay, the edges between them represent links between the routers, and the labels on the edges represent the cost of using that edge. Okay, right? So is that good? So basically, we're going to abstract everything as a graph, and then we're going to operate on the graph. So are we good here? Yeah. So this is going to be our framework on which we build the two routing algorithms. Now, let me see here. Okay, so we're going to talk about. So I told you that the label on an edge was the cost of using that edge. It says cost in quotes. Cost is a general term. It could mean many things. Okay, so that's the cost of an edge. The cost of a path is just the sum of the cost of the edges on that path. So it's pretty straightforward. All right, so, and in routing, we're going to ask the question, what is the minimum cost path between two nodes? In this example, U and Z. Okay, so this is the routing problem. It's the algorithm that finds the minimum cost or the least cost path. Okay, now, we're going to build algorithms to solve this problem, but I'm going to convince you already know how to solve this problem. So can you tell me what the answer is? What's the least cost path between U and Z in this graph? So yeah, so you've given me the least cost. Tell me the least cost path. So you Students in the back? Hi. The last row, hello. You're in my class? Yes? Are you in my class? I had to ask because one time there were students sitting who were not in my class, right? So can you tell me here? What is the least cost path between U and Z? The graph is shown there. 4. So 4 is the least cost. Can you tell me the least cost path? Yes or no? A bit louder. U, X, Y, Z. Correct. Yeah. Right. So can all of you see that? Now there are many paths. Can I ask the lady who gave me the answer? What's your name? A bit louder. Spell it for me. Jingying. Is that correct? So Jingying, can you tell me why you came up with that? Because there are many paths from U to Z, right? Or U to Z. Why did you pick that one? Can you tell me? A bit louder? You use Dijkstra on this? Can we try something without Dijkstra? Okay, so can you just tell me why you would why U X Y Z is the least cost path? Okay, so this is good. You're giving me Dijkstra, right? Don't give me Dijkstra. Give me try. So I think you know what's going on. I want you to articulate it from just using very simple language and use common sense. So why is U X Y Z? No. Okay. You're like 2 steps ahead of me. You're too advanced, Jingying. Something simpler. Why? Yeah.
So you start at Y and look at the path we have. Just pick the lowest.
Okay. I think you guys are way ahead of me. Okay. Anyone want to give me a really simple answer? Okay. Even more complex. Yes. A bit louder. Okay, yeah. Okay, you're all on the right track. You're just ahead of me. I'm very. I was looking for something much simpler. Just look at this and say there are many paths from U to Z, right? Yeah, and because the graph is small, you can eyeball it, right? You can kind of see that U, X, Y. I mean, there are not that many paths, right? You can almost enumerate them without difficulty here. Yeah? You want to say something?
Are you looking for just looking at the smallest distance without looking at the weights?
No, I want it. So I'm trying to convince you that you know how to do routing already. And Jingying established that she knows how to do routing. To the rest of you, can you just, if I just asked you with no lecture about routing and looked at this and I've told you what the cost represents and how to compute costs, can you tell me the least cost path? Yes or no? Tell me. Yeah. Tell me the least cost path. Yeah. Yeah, why? Yeah. Yeah, so the point I'm trying to make is that if you get confused later, come back to this slide. You know how to do routing already. My experience is that people get confused later when they see equations and all this stuff. But I'm trying to convince you, preempt any confusion by convincing you know how to do routing. You know what the solution is. This gives you a sanity check. If your algorithm computations gives you an answer, you can do a sanity check, right? You don't just say, I computed algorithm and this is what I got. No, you have to understand what you're doing, right? You're solving this problem. And the fact is, on this problem, you can eyeball it. So by inspection, so Jingying, tell me the truth. Did you really run Dijkstra? Or did you eyeball it? Huh? See? I was correct. But you tried to give me the answer I wanted. You thought I wanted. No, I wanted the simple answer. So I think all of you can, we're going to learn Dijkstra. Absolutely right. We're going to learn because a computer has no eyes, cannot eyeball. So a computer, we have to give a set of rules. But you don't. You have a powerful computer that can look at this and answer the question. Okay, so anyway, enough of this. The takeaway is you understand the problem, okay? And you know how to solve it already. The algorithms are nothing but a methodical way to solve this problem under varying conditions. Okay, and we'll see what those conditions are. All right, so here are the conditions. Are we going to have a centralized algorithm or a decentralized algorithm? Meaning, do we have access to the entire network or not? Now, when you look at it, you have access to the entire network. So you like the centralized algorithm. Okay, so this is going to be the primary distinction. Right? There's a bunch of other stuff, but let's not worry about it. If you have full information, we call those link state algorithms. If you don't, if you only have local information, we're going to call those decentralized or the distance vector algorithm. Okay? And these are the two algorithms we'll talk about. So these are the two main assumptions. Do I have global information or do I have local information? Okay, so let's talk about the one where we have local information. So the assumption, the starting point, is that I know everything. I know the nodes in my network, I know the edges between the nodes, and I know the cost. I know the labels on the edges of every link. It's a very strong assumption, right? So with that assumption, you can build an algorithm to find the least cost path, right? And the algorithm is well known, right, for finding the shortest path in a graph, and it's called Dijkstra's algorithm. Okay, it's named after a Dutch mathematician. Okay, I think so. There's an algorithm. I have some pseudocode. I'm going to let's do it by example. Okay, I think the best way to understand this is through. Not even through this example, through this example, okay? And what I'm going to do, I'm gonna like regret this, but I'm going to, for the moment, remove. Oh, that's not what I want to do. Sorry. Can I? Yeah, maybe it's not so easy to get this. Okay. I think we can leave my edges in there. Assume right now there's no green edges. Okay? Can we do that? Can you erase the green edges? All right, I just have a network. So we're going to talk about the principle of Dijkstra's algorithm. Okay, are you with me? So this is my problem. I want to find the path from the least cost path from U to Z. This is the same network that you looked at and knew what the answer was. But I'm going to show you how to run Dijkstra on it. And I think some of your classmates were already alluding to it before. Okay? Dijkstra's algorithm is based on one principle. Can anybody tell me what that one principle is? Since many of you seem to know it already. What's that one principle? Anyone know? From your previous studies of Dijkstra? Be greedy. You're shaking your head. Then why didn't you say it before? Huh? Be greedy. Okay? Dijkstra, which means at every point in the algorithm, you make the best decision for you, the best local decision. Okay, so I'm at U. So right now, I know nothing. I don't know anything about the path. I'm at U. Okay? So how many options do I have? Look at this graph. How many options do I have to move forward? I have 3 options. What are the costs of those 3 options? 5, 2, and 1. So be greedy. So which one am I going to choose? I'm going to choose to add the edge ux into my, let's say, so I'm going to have a known set I'm going to have an active set and an unknown set. The active set is the set that's like in my sort of routing graph, if you will. So right now there's nothing, but I'm greedy, I add ux. So what's next? So now u and x are known, so what do? So I figure out what choices I have. What choices do I have?
5, 2, 1.
Yeah, so from u and x, I look at where can I get to from u and x. How many choices do I have? I can count 1, 2, 3, 4, 5. Does everyone see those 5 options? Right, so where can I get to from u and x? So here's x, and here's u. I can go here, 1, 2, then from x I get 3, 4, 5. Right, so I have 5 options. Now since again, 5 options, I'm going to choose the least cost option. But not the least cost edge. Since I'm routing from u, I compute paths from u. So I have 5 options, I start at u and go to those 5 options and compute costs. So which one is the least cost? So u to v is 2, u to w is 5, ux is already there. So uxv is what? 3. uxw is 4, and uxy is 2. So which is the least cost one?
UV and UX.
So I have 2 options, uv or uxy, right? At this point, you can flip a coin. You say, it doesn't matter. Flip a coin. So which one do you want to add? uv or xy? Which one? Okay, so we'll add uv. So now u, x, and v are in my active set, and I just run the same idea again. Where can I get to? And then you will find that the best. So can you see what the next best choice is? So I can go uvw, ux is already there. I can go uw, uvw, uxw, uxy. Right? So what's my best option then? Yeah?
UXY delete.
No, we haven't added y yet.
UXY.
Yeah, so the least, right? So getting to y is one of my options, and that's of cost 2. That's the one we didn't choose in the previous round because we flipped the coin and chose uv, right? So I had uxy. So now u, v, x, and y are in my active set and go on. And so what I like to say is to think of is like the back of a shampoo bottle. Has anyone ever read the back of a shampoo bottle? Like, what does it say? What do the instructions say? It says what? Yeah, it says that, correct, but it says what? Like it says after you wet your hair, you put it on. It says lather, rinse, repeat. Yeah, so that's all the lecture is. What we just did, repeat it until you're done. That's it. Be greedy over and over again. Okay? So this is how we understand Dijkstra. Yes, there's an algorithm. And so this is the next step. If you understand this, you understand Dijkstra. Right? We still haven't written code that a computer can write, but if you wanted to, you could actually put that into a algorithm, right? You could write code to do it. It might not be efficient, right? Getting it efficient takes some work, but that's computer science. That's like programming. That's software. This is idea. So anybody have any questions on the idea? It's very simple. Be greedy and keep being greedy until you're done. Right? So in this case, we've added ux. So the order was ux, v, y. Then the next one will be w. Because even though you can get uw, that's cost 5, uvw is 5, but uxw is 4, but uxyw is 3. That's going to be your next best thing. You're going to add the edge v wy. Okay, and then the next edge is going to be yz. And what this gives you, if you recognize it, it gives you a spanning tree. Okay, and this spanning tree defines your forwarding table, right? What's the forwarding table at U? So at U, I need a forwarding table. The forwarding table has to have every destination, and what interface do I forward on? So I'm at U. U has how many interfaces? 3, right? Let's call those interfaces, by the endpoints, the label of the edge. So it has 3 interfaces, UW, UV, and UX, right? So what's the forwarding table at U? So let's take X. I have what? V, W, X, Y, Z. Right? So when I'm at V, what do I forward on? Which interface do I forward on if the destination is V? Can you tell me? Yes. I asked a question. I don't need to point to you, please. If you know, just speak up. Which interface do I forward on if the destination is V? Yeah, we're always at U, starting from U. Huh? Which interface? UV. If I want to forward to W? UX. If I want to forward to X? Y? And Z? Yeah, so that defines the forwarding table. Right? So the routing algorithm gives you gives you a spanning tree which drives the forwarding table. Okay? So we've seen that we've closed the loop. Okay? If we go back here, so this was, if we want to talk about writing down some pseudocode, we need to make some definitions. We'll call C of xy the cost from x to y. D of v is the current value of the cost from u to v, the source to v. And in my examples, u was the source. P of v is the predecessor node, and n prime is the active set. Okay? So, and then this is the pseudocode, but I'll show you that here's a kind of a systematic way of doing it. Okay? So we start off with my active set only has u in it. Okay? And when I start off, now each of these columns, so this is like the step. I put my active set here, and then I have a column for every destination. Given I have a source u, there are 5 other destinations, so I have 5 columns. And what I'm going to do is, at every step, keep track of my current best cost to all destinations. And now choose the minimum one. So for example, I start with u, okay, and I have 1, 2, 3 options, right? That's why there's only 3 non-zero entries here. Y and Z are not connected to u. So that's why there's an infinite here, and infinity here. Right? So this 2 corresponds to this 2. This u says, for this path, the predecessor node is u. Right? So this is 2u, this is 5u, and this is 1u. And then I choose the least cost one. Right? Just like we said, we choose the least cost edge. Now, I figure out, again, the least cost to all. Now, I already have x, so there's nothing here anymore. I find the least cost to all other destinations. Now, once I add x, w is suddenly, y is accessible. Right? So this infinity here now becomes something. But z is still not accessible. So that's still an infinity. So what do I do? To get to v, I have 2. This is the best one. Now x is already gone. W, before it was 5u, right? Because I could only do that. But now I can do that. So you see, and this is cost 4. So see, this changed to 4. And this x tells me which path it is. It's a path through x. Right? Because I already added x into my active set. So by writing the predecessor node, I'm telling you which path I'm taking to W. Right? It's a cost 4 path through X. So that's why this is 4X. And then this is 2X, because I can get to Y like this. Okay, and then again, the same way we flip the coin, right? Remember I told you at the second step, we had 2 choices. The same way. So here it is explicitly. I can choose any one, and in this one I chose Y. And then in this step, so you chose Y. Now, once I add Y, suddenly the cost to W, instead of being 4, is now 3. Right? So we see 3Y here. And suddenly Z is accessible now. Okay, but I still have the path to V, so I'm going to add that next, and so on. Okay, so this is just a systematic way of running Dijkstra. Okay, but I want you to understand the principle, not a mechanical, a mechanical recipe. So, good. Any questions about the shortest path algorithm? Yeah? So, with the gentleman in the back, did you have a question? No? Okay. So, any questions on this? Okay. Okay, so, yeah, and then, so from the forwarding table, we get, from the shortest path spanning tree, we get the forwarding table. Okay? A couple of things. If you implement Dijkstra naively, right, you need about n squared computations. Why? Because if there are n nodes in the network, for every n nodes, you need to sort of compare to approximately linear in n number of nodes. Right? So you get approximately n squared comparison. So the complexity grows as the naive computation. It turns out you can reuse previous computations. Okay? Because remember, you're doing this, you're reusing a lot of you're computing the same things multiple times. If you reuse them, you can get it down to n log n, right? Which is roughly the complexity of sorting. Okay? I think I won't say too much about the next point, which is the link cost. It turns out you can, in my example, the link cost was static. Now, you could imagine a situation where the cost is dynamic and depends upon the traffic being carried on that link, right? Kind of like ERP, right? ERP is based on like time, but the idea is that ERP is the electronic road pricing, like the tolls on the road. They increase at certain hours of the day. So in that case, if the dynamic pricing, if that situation comes in, you can get weird behavior. Okay, that's all I'm trying to say here. But I think the important thing here is I was just talking about complexity. Okay, the other assumption that we made here that I want to point out to you, okay, it's in this graph. If you look at all of the labels on the edges, what can you tell me about them? Do they share something in common? What can you tell me about all the labels? A bit louder? Yeah, they're positive. Or it would turn out that the correct idea I need is they're non-negative. But yeah, these are all positive. You're correct. Right? And what you can show is that Dijkstra works exactly when you have non-negative edges. Okay, so when you have non-negative edges, so first of all, can you see something about? Can you tell me? Can you answer this question? Will Dijkstra's algorithm always terminate? Will Dijkstra's algorithm always terminate? Suppose I have non-negative edges. Will the algorithm terminate? Like, will it end? Will it stop? Or will it end up going on forever? What do you think? Huh? Yeah, will the algorithm terminate? Will it end? Yeah. So will it end? Yes or no? It won't end. Okay, so explain why what I explained won't end. Will the algorithm terminate? As in, if I run the algorithm, will it eventually stop? Or will I keep going on forever? Can you give me an example? Well, we encountered that here, right? Remember, uv and uxy have the same cost. We finished. So you're almost there, maybe. So the question is, again, with non-negative edges, will the algorithm terminate? Yes. With negative edges, will the algorithm terminate? Confirmed? Huh? Yeah. A bit louder? Exactly, right? If you have a negative loop in the graph, then the so that's a very good point you make. If you have a negative loop, we have a much bigger problem, right? Anyone know what the much bigger problem is? It's not the fact that Dijkstra won't terminate. If you have a loop in the graph that has a negative cost, what's the big problem? Yeah, so you're correct. Dijkstra won't terminate, but I'm trying to say go above. There's a much bigger problem. The problem is not that Dijkstra won't terminate. It's not a problem with Dijkstra. It's another bigger problem. Do you know? You cannot find the least cost path, but almost. You're right. I think you know what you're saying, but I want you to rephrase it. Yeah. The computation will be wrong. It's a bigger problem. You're on the right track. Yes. The least cost path makes no sense. So there's no point writing an algorithm to compute something that doesn't make sense, right? That doesn't exist. Yeah, okay? But that's excellent. That was going to be one of my examples later. So again, you guys are really good. You kind of preempted me. So, yeah, so these are some tricky cases with Dijkstra. So I want to get back to what Daniel said. You said something about it gives a wrong answer, right? So if you have negative edges, but no negative loop, will Dijkstra terminate? Yes, but it may not give you the least cost path. Why? Anybody know? I'll do examples later, but anyone know why? Because Dijkstra is, what was the first principle? Greedy. It doesn't look at the future. If there's a very big, large negative edge in the future, right, you can't exploit it. Now, you can, of course, modify Dijkstra by backtracking, right? You can say, I'm going to allow looking backwards, right? But that's a modification of Dijkstra. And you can actually show that the worst case complexity when you modify, when you allow that, is no longer. So anyone know what the worst case complexity here is? If we don't allow Dijkstra, so Dijkstra we said was approximately n log n, or naively n squared, right? What's the worst case complexity if I don't allow Dijkstra? You basically have to compute all paths, right? And then, yeah. And anyone can guess what the complexity of that is? Sorry? Square of the vertices. No, but n squared is Dijkstra. Yeah, n squared is Dijkstra. It turns out you have to do a lot more work, right? In the worst case, an edge is either in your spanning tree or not, right? So you count the number of edges, and it's 2 to the number of edges. You can make that a little bit better, but not much better. Okay? You still end up being exponential in some input parameter. So the worst case is that. You can show backtracking. In the worst case is that. I can give you scenarios where you have to backtrack and essentially you have to search every path. Now the average case complexity can be better. Right? But remember, backtracking in our terminology is not Dijkstra. It's modified Dijkstra. Okay, vanilla Dijkstra is what we discussed. All right? Now, I know, I think in some algorithms classes, they call this Dijkstra, the backtracking. Okay? But, this is just semantics. We'll call Dijkstra vanilla Dijkstra. Okay? Yeah? Sorry? Are you asking what's the meaning of a negative edge? Or are you asking, there's no negative edge here? So suppose I change that 3 to a minus 3. It could potentially be in an engineering problem, you might not. Right? But as a graph problem, you might. Right? When you just talk about graphs, you might. Yeah? Can you take out imaginary numbers? Well, it depends on how you set up the problem. I don't want to say no, because I could imagine a framework where you do. Yeah. But, I can't think of one in an engineering context. Okay? If you have a real network, you're not going to talk about negative edges or about imaginary edges. Okay? But I do want you to see the bigger picture. I want you to know what happens with negative edges. It's about understanding Dijkstra. Okay, so if you have negative edges, the algorithm will, may terminate and it may give you the wrong answer. If you have no negative loop, it will always terminate. If you have non-negative edges, you get the right answer. Okay? I'll give you some examples later. Okay, so are we good with Dijkstra? We understand a little bit about it, right? Okay, and we understand that, so the output of Dijkstra is a shortest path spanning tree. So by the way, if I label all the edges as 1, let's say all the edge labels were 1, what does Dijkstra give me? If all the edges are 1, labeled as 1, the number 1, what does Dijkstra give me? No. Sorry? Yeah, it's minimum hop routing. Hop count. Right? Because every time you go, you're adding 1. So I'm counting the number of hops. Right? If this could be dollar cost, this could be delay. Right? If, let's say, this is the delay on an edge, right, then I get minimum delay routing. Okay, so the interpretation, right, in the general case, we just call it a cost. We can give it meaning. This could come from something. It could come from labeling as delay, then Dijkstra gives me minimum delay routing. If it's 1, I get minimum hop routing. If it's a cost, minimum dollar cost, I get a minimum dollar cost routing. All right? And remember, I know everything. When you do this, you know the entire network topology. Right? So for example, can you do Dijkstra on the internet? Somebody said, no, why not? Give me one reason why you can't. It's not scalable, so what does that mean? Can you elaborate? So you're saying, I may not know all the data because it belongs to different companies, right? Can somebody give me another reason why I might not be able to use Dijkstra on the entire internet? Yeah, sure. But let's assume it's static for a small amount of time. In that time, can I run Dijkstra? So one was I may not know, but now let's say I know. Give me another reason. Yeah? Yeah, forget about backtracking. Just vanilla Dijkstra. Yeah, I'm saying, let's say, so that was the comment here that you may not know. I'm saying, so that's one point. But let's say now I know what I need to know. Then why might it be unfeasible to run Dijkstra on the internet? So one is knowledge, yeah? Yeah, so that's true, it could change. But let's say it stays constant for 10 milliseconds. We'll make that assumption. So now I can run it. Or I can possibly run it. Why might not I be able to? Do you know? Yeah, hang on. Do you guys know? Is it hard to run Dijkstra? Like, how complex is it? Do you remember? Yeah? You might not have any space in your forwarding table. Okay, but let's say you do. Let's say memory is not an issue. Why is it not efficient? Yeah, yeah. The point is complexity, right? Internet has millions of nodes, and we saw that the complexity grows as n squared, right? I'm not saying it's not possible, but it is a potential reason it could be infeasible. Not knowing makes it impossible, but knowing but having to scale it. When you said scalability, I thought that's what you were saying. It doesn't scale to the number of nodes. Okay, so yeah. Tell me why? Like, what do you mean? No. So are you talking about backtracking in computing the routes, or backtracking in actual transmission? No. Remember, in Dijkstra, I know everything. Yeah, I know everything. So I have to route to every node. So I have to go to every dead end. Even if there's a node that's a dead end, I have to go there because that's a potential destination. Yeah. Okay, so good. So we saw that on small networks, you can run Dijkstra. On large networks, it's impractical. Okay, so we need another idea. Dijkstra itself is not enough. Okay, it doesn't solve routing on the internet. What we do is this. We take another strategy called distance vector. And distance vector is an algorithm that requires, maybe let me not go here for a second. Distance vector is another routing algorithm. Okay, remember, link state or Dijkstra was one, required full topology information. Distance vector only requires information about your neighbors. It requires local information. So this now scales to the internet. Does that make sense? Okay, so we're going to study a second algorithm that can help us scale. Okay, and this only has local information. And just like we said, Dijkstra had one principle, which is be greedy at every step. Distance vector has one principle. Right? If you know me, if you've figured out by now, we try to get to the core of the idea. Right? So for distance vector, the core of the idea is the Bellman-Ford equation. Okay? And this is also the basis of something called dynamic programming. So if you're interested, you can go look up dynamic programming. Okay? But it doesn't matter. I just put that there so you can connect it if you have studied this before. But it's okay if you don't know what dynamic programming is. For us, this equation in red that's boxed, this is called the Bellman-Ford equation, and it's the main principle of distance vector algorithm. So let's figure it out, okay? Let's see what this is. Let's, for the moment, forget this, and let's go through this sort of a thought experiment with me, okay? So let's say I'm trying to route to someone in the back. You, hi. Yeah, I'm routing to you. You are my destination, all right? And I only know information about my neighbors. So you're my neighbor? You're my neighbor? Hello? Gentleman in the blue shirt, you're my neighbor? Okay? So 1, 2, and this lady here. Hi. You're my neighbor. Okay, so I have 3 neighbors. I'm trying to route to, tell me your name, I forgot. Spell it? S-I? Oh, Sid. Okay, I'm trying to route to Sid. Okay, so I have 3 neighbors, and I'm trying to route to Sid. Now, what can you tell me? So this is now my question to you. What can you tell me about every path from me to Sid? This is the thought experiment. Every path from me to Sid, what can you tell me about it? Yeah? No. I mean, you're on the right track, but tell me something much simpler. Yeah, I mean, you're on the right track, but you're like getting ahead of me. What can you tell me about every path from me to Sid? There's a common characteristic of every path that goes from me to Sid. Is a tree. Okay, I mean, a path is a tree, right? Because it's a single path. So every path must do what? Well, it must start at me. It must end at Sid. What else? One other really important characteristic. I have 3 neighbors. That's the hint. Can you tell me? Yankees. Are you a Yankees fan or are you a baseball fan?
No, I just bought
You just like the hat. I like the hat. I'm from New York, right? So I like the New York Yankees. Okay. So yeah. Yeah, a bit louder. Every path from me to Sid must go through one of my neighbors. Correct or not? Yeah. That's it. Now that observation is that. And if every path must go through one of my neighbors, which is the best path to take? Well, I asked, and now we get to what you're saying. I find out what your cost to Sid is. I find out what your cost to Sid is. I find out what your cost to Sid is. Right? And I add my cost to each of your costs. My cost to you plus your cost to Sid. And so on. And what do I do? What do I do? I have 3 costs now to Sid. Choose the smallest one. That's that circled, that squid. Sorry, the equation in red is just that. Okay, it says that, so so I'm X, Sid is Y. The least cost from me to my destination, from X to Y, is just the minimum of all my neighbors V. V are my neighbors, 3 neighbors. Minimum over V of what? My cost to my neighbor plus my neighbor's cost to the destination. So that's it. This is distance vector. If you can understand this, just like if you understand how to be greedy, you understand Dijkstra. If you understand this, you understand distance vector. So if you don't get it, let's not move past this. Because then we get into some details, but this is it. Anybody want me to repeat? Is everybody good? Yeah? How about this gentleman who's the farthest from me? Hi. Are you okay? All right. Okay, so yeah, and then I go through a bunch of, so like, again, costs and everything also add up, just like before. So here, this is the same graph as before. So now if you look at, so I need to know from my neighbors. So I'm trying to route from, I'm at U, I'm trying to route to Z. So I have 3 neighbors, V, X, and W. I need to know my neighbor's cost to Z. Now, how do I know that? I ask them. How do my neighbors know? They're also running distance vector. Does that make sense? Everybody's running distance vector, but separately. Okay, so they have a current estimate. So from my neighbors, I know dVz, dXz, and dWz. So this is the cost from V to Z, X to Z, and W to Z. Okay? And you can verify it. If you look, what's the minimum cost from V to Z? the minimum cost is what? 2, 1, 2, right? It's 5. And xz is 3. xyz, and wz is not 5, but rather wyz, or 3. Okay? And the idea is they're running distance vector themselves, so they know. Okay? And the Bellman-Ford just says, you ask its neighbors, hey, what is your cost to z? Well, v says my cost is dvz. And also u knows its cost to its neighbors. So it looks at the cost from u to v plus dvz and so on. It computes these three metrics and it gets 4, which we knew before, right? It's uxz. But now in this instance, it doesn't need to know the whole path. It just needs to know who the next hop is. And the next hop is who? Is, in this case, is what? The next hop is the middle one, x. Right? So that's the same thing that we got before, right? If I have a packet destined for z, I'm going to route on ux, right? So this gives me the same information. Right? It lets u compute its forwarding table. Okay? So do we see how distance vector works? Okay? Yeah? Yeah?
How is dynamic programming different from
dynamic programming is different
linear programming?
from, yeah, it's very similar. There's an idea called memoization. Yeah, dynamic programming is just that, right? Yeah. So, I mean, it's just a way of reusing computations you've already done in a smart way. Yeah. But now it becomes much more interesting. Usually in computer science, you talk about like memoization. But in engineering problems, you have stochasticity. To do stochastic dynamic programming, that's where the power of dynamic programming really comes in. Yeah, to take into account randomness. Typically, dynamic programming, the first step, the way you often learn it, is just a way of keeping track of what you've already computed and reusing it. Right? So like for example, if you want to compute the Fibonacci numbers, you can do it by reusing, right? If you compute a certain Fibonacci number, the next one, you don't start from scratch. Yeah. Capturing that is called dynamic programming. Okay, but bringing in stochasticity is where it really takes off. It gets really interesting. Okay, all right, so let's do this. I think I have a super gory example for you. So distance vector, again, the idea is this. Every node is running distance vector, meaning every node is looking at its neighbors and trying to create a routing table independently. And it's when, so I'll show you what happens. When I make an update to my routing table, I share it with my neighbors. Okay? So for example, each node sends its own distance vector to its neighbors. When it gets a new update, it recomputes Bellman-Ford and then sends, if anything changes, it sends it out again. Okay? So let's do a gory example. Okay? So I have a small network here, XYZ. This is the labels and the costs on the edges. So when I start off, okay, I know nothing. So all I know is my cost to my neighbors. So now on the left, in the very first column on the left, I'm looking at at what x is doing, what y is doing, and what z is doing. So this, everything that's in the first row is happening at x. Everything in the second row is happening at y. So being computed by y. And everything here is being computed by z at z. All right? Now what x does is it's going to maintain its routing, its costs to all destinations, right? So x to x is 0, x to y is something, and x to z. So this is dxy, and this is dxz. So x maintains that. Now x also maintains y's costs. Okay, so this second row here is x's information about y. This third row here is x's information about z. Okay, now at y knows, right? Because initially, so if you look at x here, this 0 to 7 comes from the fact that x knows this and x knows that. And y also knows this. Okay, so do we get the starting point? So x and y know the cost to the neighbor, so they can fill in their initial rows. Okay, and they don't know anything about anybody else. They haven't yet shared information. So now, clock ticks. Then they share information. Okay, so what's going to happen is, like these two guys. So y knows this, and z knows this. It's going to share this information with x. So this comes here to x, and this comes here to x. And what does x have to do? What is x going to do now? Run. What? There's only one, I told you, one principle. So what is x going to do? Run. Run what? Can you tell me? What is x going to do? What is the action x will take? Do you know? If you don't know, you can say no. Yeah, I'm talking to you. Yes, hi. What's x going to do? Yeah, just no. Run what? Run. What do we call that equation? Yeah, say it louder. It's going to run Bellman Ford. Yeah, exactly. So that's all I want. I don't want you to tell me what it's going to do. I'll tell you what it's going to do. Okay, so this is what it's going to do. It's going to now, it got these two pieces of information. Now it can run Bellman Ford. Right? Because now it knows this is dyx and dyz. This is dzx and dzy. And it can use those here, right? Okay? And it runs Bellman Ford, and it can now, for y, the cost to y, it can update that to 2. Okay? Why? Because it knows that I'm at x here. I know that that I have a route 2, right? So this is its own route to y, and this is its neighbor's route to y, right? But the neighbor's route to y is more, because why? I have to go 7 plus 1. And that's 8. And that's greater than 2. So this remains as 2. But let's look at the route to z. X to z is 7. What is y's route to z? So what is y's route to z? 1. And x's route to y is 2. So this will get updated to 3. Right? So this 7 became updated to 3 because I got more information, right? I got information that y has a route 1 cost to z, right there. Okay? And then we do the same thing. We just share information and run Bellman Ford. So that's the idea. I run Bellman Ford. If I have an update, I share with my neighbors. If my neighbors get if any node gets an update, you run Bellman Ford. And if you update your own stuff, you tell your neighbors. And you just repeat. And the beauty of this is that you can have these updates happen on a synchronous basis, on a clock. You can have it happen synchronously or asynchronously, and under very, very mild conditions, this converges to the right answer. That's the power, sort of beauty of this. This sort of distributed algorithm. I don't know full information. I know only local information, everybody will converge to the right answer. Okay, are we good with this? Okay, in here, I stop here because at this point there are no more updates. Like so in the second step, this changed and this changed from here. This 201 remained the same, right? But this changed and this changed, so I tell my neighbors, but that doesn't change anything for them. So there was no update, right? 0, 2, 3 remained, 201 remained, and 310 remained. So I've stabilized. Okay. Now on the internet, you have a protocol that even though things don't change, it periodically updates. Okay. Just sort of as a heartbeat. All right. But the general idea is that you stop. Now we'll see later that you can still have changes happen, because the cost from me to my neighbor could change. Right? Like for example, you're my neighbor, maybe my link to you breaks. My link to you breaks, that cost went to infinity. And that's a change. I'm going to rerun Bellman-Ford and update my neighbors, and that will trigger off a series of updates. And eventually, hopefully, it stabilizes. Right? You probably know what's coming, right? Because I said hopefully. So I hope you know that was like a forewarning. Any questions on this? So link state or Dijkstra, one principle, be greedy at every step, but you need to know full information. Dijkstra, distance vector, you don't need to know full information. You know neighbor information, and the principle is run Bellman-Ford. Means find the best neighbor. Any questions? Okay, so all right. Link costs can change, right? I told you that once the network stabilizes, things can change, and there's some bad news. Some good news and some bad news. I'll give you the good news first. All right. The good news is that when costs go down, for example, if the cost between, so let's say my original one is the one in black, and let's say the network has stabilized, right? We saw that on the previous page. It stabilizes in 2 or 3 steps, right? Let's say 4 goes to 1, right? So the cost between x and y goes from 4 to 1. I call that good news because things don't usually cost less, right? The price of things usually don't go down, but let's say it goes down. I call this good news, and you will see that good news travels fast, meaning that everybody will learn of the good news, and the good news is that good news travels fast. All right, and so what's going to happen here? Well, tell me what's going to happen. X is going to notice the change. Right? X will notice that, oh, my cost to y went to 1. So what will X do? There's only one answer to that. And he knows what it is. Hi. Yes, you. Yeah, you. X will do what? No, you already know the answer. Don't overthink. X will use the same answer as last time. X will run. Yes, X will run Bellman-Ford. Okay? Next time the answer is run Bellman-Ford, I'm going to ask you, okay? All right? You're going to get this one way or another. Yeah, it's a change. Something changed. So X has to run Bellman-Ford. And then, if any of X's distance vectors changes, it's going to inform its neighbors. And what will its neighbors do? Do what? Do what? Yes. Okay, so let's say at time t0, okay, I did it from y's perspective. It doesn't matter, right? At t0, y detects the link cost change. It updates his distance vector, which is running Bellman-Ford, informs his neighbors. Then at time t1, z receives the update from y, updates its table. It computes a new least cost to x, and it sends its neighbors its new distance vector, and at this point, things stabilize. Everybody has learned of the good news. And the good news is that it happened quickly. You see the two good news, right? Costs went down, that's good news. And the other good news is that everybody learned of the news quickly. I told you I'll give you the good news first. Right? Now the bad news. The bad news is that bad news travels slowly. Meaning, when costs go up, right? If the cost goes from 4 to 60, not 4 to 1, go up, that's bad news. And the bad news for us is that this information takes a very long time to stabilize. Okay, so let's see what happens. So don't worry about the bottom here, okay? And don't worry about all this stuff. Let's look at this, and let's talk through what happens. Can we do that? So I need everybody with me now. All right, we're going to do a thought experiment about what happens here. Okay, I have to tell you, I told you that when things are straightforward, I will tell you straightforward. When things are a little bit tricky, I'll tell you. This can be a bit tricky, so please pay attention. Okay, so we're starting off with like 4, 150, everything stabilized. 4 goes to 60. Let's see what happens. Okay, let's say y learns of this change. Okay. What is y going to do, my friend? Yes, it's going to run Bellman-Ford. Okay? Now, so y thinks, oh, okay, my route to x just went to 60. Okay? But what does y know? Remember, things have stabilized from before. What does y know? So you have to remember, what is y keeping track of? Let's go back here. What is y keeping track of? This is y's own distance vector estimate. So after the stabilization, this is y's own distance vector estimates. What else is y keeping track of? Yeah, x's distance to destinations as well as z's distance to destination. So in this example, what does y know? It sees a link cost change to x. But what does it know? What other information does it know? It knows that x is its neighbor, and it knows its cost to neighbors went up high. But it has another neighbor. Yeah. And what does x know about z? That's what what is x keeping track of? It's keeping track of z's distances to all destinations. And in particular, it knows z's distance to x. Right? So before the link cost change, what was z's distance to x? 5. So this is what y knows, right? So y knows that my friend z has a cost 5 path to x, and y thinks my own cost to x just went to 60. I'm going to use my friend my friend z. And how is it going to update how is y going to update dy x? It's going to go through z, right? So what is it going to update dy x to? 5 plus its own cost to z, which is 1. So he's going to update it to 6. Now, let's just ask, was this the right thing to do? Can you give me a show of hands? Was what I just said about y doing is the correct running of Bellman-Ford, but we see the situation. Is this the right thing to do? Yes or no? Tell me why. Yeah. That right there is the core of the problem. Right? z's path to x goes through y, but y doesn't know that. So what is y going to do? Once it updates dyx to 6, it's going to tell z. What's z going to do? Oh, my friend y has I have a cost 50 route to x, but my friend y tells me she has a cost 6 route to x. Oh, I'm going to use that. I'm going to run Bellman-Ford. My cost to x is 1, so what is z going to update dzx to? Do you know? Yeah, tell me. Yeah, you. To what? dzx will get updated to what? Yeah. To what? No. Because 50, it's going to compare 50 to what? 6 plus 1. So which one will it choose?
50.
Which one's smaller? Right? dzx. What is dzx? This is important. Okay. So let's do this. So before change, before the change, dy x equals what? Before the change, what's dyx? Sorry, no, you gotta say at z. dyx is 5. And at y, what's dzx? What is it? dyx at z, dyx is 5. And yeah, and sorry, at z and dzx is also 5, right? Yeah, should be 4. Sorry. Correct. Yes, thank you for that. So this is before the change. After change, meaning after x, y, this link changes to 60, then what's going to happen? Well, again, we have to do it at y. So y thinks dzx is 5. So it's going to use that information. And I was pointed out that's wrong, but it doesn't know that. Y does not know that z is using y to get to x. So unfortunately, y will use it. So what will y update dyx to? To what? You update it to 6. And then at z, what will dzx go to? Well, I mean, so y will tell z, oh, my dyx just went to 6. And so dzx will go to 7, right? 6 plus 1. Then, what's going to happen at y again? dzx just went to 7. Yeah. And they will just ping pong back and forth until what's going to happen? Until what? Yes, until dzx going through y becomes bigger than 50. Then z will say, I have my own path, which is less than 50. and then everything is good. And but this will take a long time, right? The numbers are, we're just ping-ponging back and forth. That's why I wrote it takes 44 iterations, because we start off at dyx equals 6, and I'll just ping-pong back and forth. Yeah?
What is x doing at this time?
Yeah, x is carrying out its own, it's going to go through, yeah.
It feels like it should do like a parallel thing with z or y.
Well, it knows that its path to y just went to 60,
Yeah.
so it's going to look at z,
Yeah.
and it's going to route through z,
Yeah.
right?
That immediately.
Yeah, so, but that doesn't affect what y and z do. But it's going to recover, it's going to go through, its route to y will be 51. So dxy is 51. Yeah. Okay? Yeah. But y won't use it because its cost to x is 60, and z won't use it because its cost to x is 50. Right? So it's not going to use those. It thinks it has better routes through y, and y thinks that it has better routes through z. So they'll just ping pong back and forth until, as I said, z's route through y goes above 50. Then it will take its own route to x. Okay, so this is what I mean by bad news travels slowly. And if the link, in this instance, you won't get there are situations, right, where if a link breaks, you will count to infinity. You will never stabilize. So that's why this problem is called the count to infinity problem. Okay? If it won't happen in this case, but I'll show you next time some simple situations. In fact, if we just take situation of 3 nodes, 1, 2, 3, right? Just 3 nodes in a line, and you break one of the links, and you work through, you will see that you'll count to infinity. So this is a huge vulnerability of distance vector algorithm. So we look for solutions. One solution, so was your classmate in the back, hi, said the core problem was that y does not know that z is using y to get to x. So one way to potentially solve this problem, I say potentially, is called Poisson reverse. If z routes through y to get to x, then z lies to y and says its distance to x is infinite. So y will never use z to get to x. Does that make sense? You lie. Z will lie to y. So if z is going to use y, I don't allow y to use me to get to the same destination. That's called Poisson reverse. And can you guess if this will solve the problem? It will solve the problem here, but will it solve it in general? The answer is no. Because this is a simple example. It turns out this problem can happen even with nodes that are far away. It's not limited to situations like this. And Poisson reverse is only a local lie. There's only one solution to this problem. Can anyone guess? It involves modifying the protocol. I'm curious if you can guess. You still share everything as before, but you share one more thing. Can you guess what you share? Right now, we are just sharing costs. What are we not sharing? Yeah. Did you say path? You said path, but did you say path too? Mr. Yankees. Yeah, but not number of nodes, but the actual path. Yeah. So if you append a path, right, then all the node has to do is before it chooses a route, it checks if it's in that path. If it's in that path, you don't choose it. And that's exactly how distance vector is implemented on networks. Okay, you append your path to the information that you send. So Z will tell Y, it won't lie to Y, it will just tell Y I'm using Y. My path to X is ZYX. Then Y is going to look at it and go, oh, okay, I'm not going to use Z because I see myself in the route. In getting to X, Z is using Y. So Y will look at Z's route. If it sees itself in the route, it eliminates that route. And this solves the count to infinity problem. Okay? So are we good with this? So it just involves a little bit of thought experiment, just figuring out what every node does, and you should be able to see the problem. Okay? Any questions? Yeah. Can Y or Z not inform who?
Y or X informs Z about the change. Because we do it periodically.
Because this is a local algorithm. Okay? And remember, in this instance, this might solve the problem. But imagine it's a big network, and a link breaks somewhere else. Now, if a link breaks somewhere else, not only the nodes near it do count to infinity, every node does. So if you suddenly start to say this change, you want to float it through the network, that becomes like link state now. It's exactly what happens in link state. Like in link state algorithm, I told you every node runs Dijkstra, but every node needs to know the entire network. How do you get it? There's a dissemination stage where you flood the network with all the information that every node needs. That's what this will be doing if you start to do it. You essentially turn this into link state. The reason this scales is that you only know local information. But because you know local information, you're vulnerable. And I pointed out to you what the vulnerabilities are. Any other questions? Okay. Okay, so something about, so complexity, it turns out that convergence is an issue, right? It takes about n squared. Okay, so link state was n squared. For distance vector, actually the convergence time can vary. It depends a lot on the topology. Because you'd have things like routing loops, count to infinity, and so on. And as I said, you fix it by doing path append. What else? Yeah, so for link state, as I told you, each node is computing Dijkstra, right? In distance vector, each node is computing distance vector. So keep that in mind, okay? So if you get wrong information, you can compute wrong routes. Okay, it's not going to happen in the small networks we have, but you could imagine, as some of you pointed out, the network can change. So by the time I get information to compute my routes, the network could have changed. I could potentially have stale routes. Okay, so okay, so I think what I'm going to do is so it's about 24 after. I think I'm going to just maybe continue for a little bit longer, and then we'll stop. We'll stop a bit early, and then you can ask me questions. Okay, rather than take a break and extend. Okay, if that's okay with you guys. So what I want to point out here is that in large networks, you have to actually combine the two ideas, okay, of link state and distance vector. Okay, so for example, when you have so the internet is actually broken up into smaller subnetworks called autonomous systems. And autonomous systems are like sets of routers owned by specific ISP. So for example, the Singtel network is an autonomous system. The ISP in some country is an autonomous system. Okay? Now, within an autonomous system, you can run algorithms like link state because all those routers are controlled by the same entity, by the same ISP. Okay? But between autonomous systems, it's very difficult to run things like link state. So usually it's a distance vector protocol that runs between autonomous systems. Okay? So also when you have an autonomous system, You have these autonomous systems. You have, and remember, they're run by different companies. So you have the idea of an algorithm that runs within the autonomous system, intra-autonomous systems, and algorithms that run between autonomous systems, inter-autonomous systems. Okay? And and both these can be different, and in fact they are. So for example, what we really have on the internet, because it's architected as multi-tier, right? You have autonomous systems, and you have within an autonomous systems, and then you have networks of autonomous systems, right? It's a two-tier network. You have a intra-autonomous system algorithm and an inter-autonomous system algorithm that drive your forwarding table. Okay, you actually have two mechanisms. Because if your destination is outside the autonomous system, the inter will take over. If it's within, the intra will tell you what the next hop is. All right, so the example, yeah, and the job of the intra is to find paths within the autonomous systems. The job of the inter is to find paths between. Okay? So for example, here I have 3 autonomous systems, 1, 2, and 3. Okay? If I want to get to, so if I'm in AS1, I have to figure out how to get to the autonomous systems 2 and 3. And then I need to propagate this information to all routers in AS1. And that's the job of the inter-autonomous system algorithm. Okay? The intra we've already done. That's what was done before. Right? We were always talking about like running Dijkstra or distance vector within an autonomous system. Now, between autonomous systems, there's, if I want to get to destinations outside. So for example, here I want to get to some subnet X far away here. Right? It's the job of the inter. So for example, AS1 learns that this subnet X is reachable through autonomous system 3, but autonomous system 3 is accessible through router 1C. So anywhere in this subnet, if the destination is subnet X, the next hop, or you should be routing to 1C. Okay? But you need to get to 1C. How do you do that? Using the intra. The intra will tell you what the next hop is to get to 1C. Okay? So we see that there are these two mechanisms. Okay? All right. So now the last thing I want to talk about here is so as I mentioned, in the internet we have the implementation of Dijkstra, which is OSPF, Open Shortest Path First, and RIP is the implementation of distance vector. So for example, so RIP is distance vector, OSPF is link state. There's also a proprietary intra algorithm by Cisco, which we're not going to study here. Okay. Now, I'm not going to go through RIP and OSPF because they're exactly what we discussed. Okay. But I put the slides here because I tell you the parameters, right, that RIP uses and OSPF uses. What I'm going to do is I'm going to jump to BGP. So BGP is an inter-autonomous system routing protocol. So BGP stands for Border Gateway Protocol. And the goal of BGP, as I said, is to figure out how to get to subnets outside your autonomous system and to propagate that information to all nodes within the autonomous system. Okay? The other thing that BGP does, in addition to getting the reachability and propagating that reachability, is BGP brings in policy. Okay, we haven't seen that up till now. Right now, we've only been talking about minimizing cost, right? Least cost routing. Right? It turns out that there's a parallel set of considerations that are not about technical performance, but rather about policy. and BGP tries to take care of that. So for example, like this is what I was saying before, that you have, an internal BGP is to propagate the information within the autonomous system. eBGP figures out reachability between autonomous systems. And now you might wonder, why do I have two different intra and inter type of algorithms? The primary reason is that is policy. Because these autonomous systems are owned by different organizations, they have to kind of have a contractual agreement. Okay? And in that contractual agreement are, clauses about how much traffic one might carry and all that good stuff, and what the cost is for carrying your traffic. And all that gets folded into BGP. Okay, so as BGP is looking at reachability and propagating that reachability information, it takes into account policy. The other thing, of course, is at scale, right? We saw before that you can't run link state on very large networks. It's infeasible, right? And sometimes you might not even have the information to run link state. And on small networks, you can do link state, get high performance, not suffer any of the vulnerabilities of distance vector, right? But on larger networks, you cannot, right? And so BGP is a distance vector type protocol. Okay, so what I want to do is I want to end here. Okay, we're going to end talking about at least about unicast routing. When we come back on Wednesday, I'm going to do two things. I'm going to finish routing. We'll talk about broadcast and multicast routing. Okay, that's number one. Number two, I'm going to show you an example of how you can understand events in the real world from some of the things we learned in this class. I'm going to talk about a situation where YouTube was hijacked. Okay, that's the second thing. And the third thing is I'll do some problems with respect to routing. Okay, some additional problems talking about like some of the negative cases about for link state, and any questions you have on distance vector. Okay, we'll do these three things when we come back on Wednesday. So you should now be in a good shape to do homework number 3. All right. I think anything on broadcast and multicast you can take a read. Can I check? Did you all get my email about the due date? So when was the new due date? Yeah, I just moved it by 1 week, right? Okay, so you should, by today, I think you're in good shape to do it. Definitely by Wednesday. If you have any questions, please, you can ask me now, or you can ask me on Wednesday about homework number 3. Okay, and then our quiz will be the following week. Okay, we're going to do it. I'm going to do it on. Did I sent you email about it, right? About the quiz? Yeah, so it'll be on Wednesday next week. Okay, and on Monday we'll have more problem solving, and we'll do some more activities, and I'll answer any of your questions that you have. Okay, by Monday I should have released the solutions to all the homeworks and stuff. Okay, all right. Thank you very much.